Hello physics students. In this video, we're going to begin our third and final portion of this long magnetism topic. Now in the first portion, we studied magnetism from a very limited perspective, one that did not involve calculus. So we learned how to figure out the magnetic force of a charged particle moving in a magnetic field, both in terms of the direction using this right-hand rule and the magnitude from the formula QVB sine theta. We also learned how to find the magnetic field, but only around an infinitely long and straight wire, mu0 I over 2 pi r. That's the magnitude, and this right-hand rule gave us the direction of the magnetic field. But that was very limited. What about other shaped wires, short ones, curved ones? Well, then we had to move on to magnetism phase 2, which was the Biot-Savart law. And we learned a formula for the magnetic field around a tiny fragment of current length ds. And the formula was mu0 I ds sine theta over 4 pi r squared. So we found the magnitude, and then we also found the direction from this right-hand rule. And then we would have to integrate over maybe a straight wire segment, or around an arc, or all the way around a circle for the net magnetic field. But we could have any kind of shape. We could have ovals or whatever. Of course, the calculus would be too difficult, so we didn't study that. But it is possible to find the magnetic field for any shape or length of wire using the Biot-Savart law. We also derived the formula for an infinitely long straight wire using the Biot-Savart law. So we didn't just need to pull mu0 I over 2 pi r out of thin air. We could derive it from the Biot-Savart law. So tremendous, powerful, very useful law. Today, the third part is called Ampere's law. And so we're going to learn today the concept of what Ampere's law is, and then we're going to apply it to cylindrical symmetry. Now you're going to see that Ampere's law, being the third part of magnetism, will be very similar to the third part of electrostatics' Gauss's law. Let's take a look at what Ampere's law is. So here we are, Ampere's law for cylindrical symmetry, today's topic. Here it is. Now, remember I said when we were studying Gauss's law, or all throughout the year, every little symbol in this expression is important. Leave it off and you're going to say something entirely different, analogous to, as I said, an example in the English language. If you say, let's eat grandma without a comma, it means you're going to eat your grandmother. Whereas when you say, let's eat comma, that little tiny speck of a little arc, let's eat comma, grandma, you're inviting her to lunch. Radical different definitions with just that little comma. Same thing, you need the circle here in the integral, you need vector signs, you need this dot here. Otherwise, you say something completely different in terms of the law. So let's digest it a little bit so we understand what the concept is. We had this closed symbol. I'll talk about it in a second. But notice instead of dA, like we had for Gauss's law, we have ds. Now, when it came to Gauss's law, we were integrating the electric field EDS around an area, a surface, and it had to be closed. So we could, for example, use a box for Gauss's law, but not this box because it's open. So it had to be completely closed in shape. In other words, like if it were a membrane, it would hold air or something, no holes in it, okay? Well, here, instead of around an area, we're integrating around a ds, an arc length, a line, instead of over a 2D volume that is in three dimensions. So we're integrating over a line, and the magnetic field must be parallel to that line. So magnetic field that runs along our integration, not perpendicular, because then the dot product would be 0 if you had magnetic field and ds this way. So we got to have B and ds aligned, or at least partially aligned. And then the dot product is not 0. Furthermore, the line has to close on itself, so it can't be straight. It has to be a curve or possibly a rectangle. In this topic, the two Amperian shapes, the Amperian loops that we're going to be using are circles and rectangles. So as you can see, this circle, if I integrate around, it comes back to the same starting point. It's a closed length. Or this rectangle here, as I integrate around, I close out the length, the line closes in on itself. So these are the two shapes we'll be studying. So in this case, you would be finding, if you integrate B dot ds around this, you'll be finding the magnetic field that lies along this arc, lined up, or lined up along this rectangular arc. Not the magnetic field like this, the magnetic field running along the arc, or either one. On the other side of the equation, instead of epsilon q enclosed over epsilon 0, we've got mu 0 I enclosed. What do we mean by I enclosed? Well, for these two shapes, let me just put this down. Let's start with the circle first. So let's suppose this is our Amperian loop. The I enclosed would be the amount of current that goes through a two-dimensional surface that's bounded by the curve. So how much current, how much amperage is poking through this paper? Either direction doesn't matter. We'll talk about that in a little bit. But the current must be poking in or out of the paper, not running along it like this. And it doesn't matter if the paper bulges out or bulges in that area. It doesn't matter for Ampere's law. But that's the area involved in this Amperian loop. For this Amperian loop, it would be the amount of current that passes through this rectangular area, again, bounded by this Amperian loop, the area inside, poking in or out of this paper. And it doesn't matter where. The current can be here, middle, doesn't matter, somewhere along going through this paper. So that's the concept. The concept is that the magnetic field integrated around this Amperian loop is equal to mu 0 I enclosed going through that hole. Okay, so let's now take a look at how this law can be used with three different examples. The first one it's not really common. It's just one to sort of make some points about Ampere's law to get you to start thinking in terms of Ampere's law. So what we want to do is we want to find this integral of the magnetic field lying along two different curves, curve 1 and curve 2, which I've colored in, color coordinated. We've got 10 amps coming out of the board here, 8 going in and 3 going out. So what I'm going to do is, before I jump into the details, I'm going to create a pause to give you a chance to catch up if you need it. All right, so let's now go on. So if you wanted to find this integral directly, let me just first mention, let's suppose at a point here, I find the magnetic field caused by this wire points something like this. And then the magnetic field by this wire, so I do the right-hand rule, use mu 0 I over 2 pi r, I find this magnetic field. And then this magnetic field, I find the magnetic field over here. And you see I've got 3 different magnetic fields, all in different directions. I find the net magnetic field at all these points along the curve and integrate. That would be a horrendous calculation. So we're not going to calculate this actual integral. We're going to focus on the right side of Ampere's law to solve this problem. Otherwise, it's pretty much unsolvable. So let's start with curve 1. Write out Ampere's law. Mu 0 is 4 pi times 10 minus 7 Tesla meter over amp. Now, what's the I enclosed? Well, we've got 10 coming out of the board, 8 going in. So obviously, we're going to subtract these two because they're in opposite directions. But which do we consider positive in our Ampere's law? Well, if you look at the direction of integration here, you see that the 10 amps would, in general, produce magnetic field that runs along in the same direction as the integration by right-hand rule like this, where I put my thumb in the direction of current, my forefingers indicate the direction of the swirl caused by this magnetic field, so it tends to swirl around like this in the same direction of the integration. So I would consider the 10 amps positive. It would create positive integral of this integral. This current, on the other hand, if I put my thumb in the direction of the current into the board, I see that my forefingers will then go around this wire in the opposite direction of the direction of integration indicated by this arrow. So that 8 amps will tend to produce negative because B goes this way and the DS goes this way. When you do that dot product, you get a negative because it's like cos of 180. Cosine of 180 in that formula. So that's why I put the 10 amps positive, the 8 negative, and then I get 2 amps over here times the 4 pi, give me 8 pi times 10 to the minus 7 Tesla meters. The amps cancel away. Now, let me go on to the next example for the blue curve. So again, the left side, too hard to calculate. We're going to focus on the right side. We got our mu 0. Now we have 3 currents going through this loop. Now, you have to be very careful though, because it looks like these are in the same direction. So the 10 and the 3 should be added together and maybe minus the 8. Not so. So in order to figure out whether the currents are positive or negative in my Ampere calculation, let me just put in some arrow directions other place. So I integrate here, and then when I'm going to integrate around this loop, as I come around, I'm actually going to be integrating this way and integrating around this way and then like this. So that's my direction of integration. When I do my right-hand rule for the 10 amps, I see that over here, first of all, the 10 amps isn't enclosed here. So I'm not going to worry about the 10 amps in terms of the direction of the integration here. But over here, the magnetic field of the 10 amp goes in the same direction as this integration. So that's positive. This is negative as before. But when we look over here, the 3 amps, when I put my thumb in the direction of the current of the 3 amps out of the board, I see that my 4 fingers swirl around the opposite direction of the integration. See that? My magnetic field goes this way, the integration's going that way. So that creates a negative dot product. So that's why this 3 amps actually should be negative as well, like the 8. Okay? And so when you evaluate that, you get negative 1 in this parenthesis times 4 pi gives me negative 4 pi times 10 minus 7 Tesla meters. So let me create a pause to allow you to catch up copying these notes down. All right, one other thing I want to point out, that just like with Gauss's law, if you have a charge outside of a box, it doesn't mean that the electric field is 0 everywhere on the box, even though Q enclosed is 0 in the Gauss's law calculation. Same thing here. Even though the magnetic field caused by this wire on this Amperian loop here is not 0, the net effect is when you do this line integral, the integral is 0, because over here the magnetic field comes up, and on this side it still comes up. So you see that sometimes when you integrate around this loop, you get negative integral. You're integrating in the opposite direction of the magnetic field. And then later you're integrating with the magnetic field, so you get negative integral and positive integral cancels. It's not that B is 0 all along this Amperian loop. It's just that this integration comes out to be net value of 0 along an Amperian loop because I is outside the loop, not inside the loop. Okay, so just a little concept consideration. So that's example 1. Now what we're going to do is move on to 2 more examples where we actually use Ampere's law to calculate what the magnetic field is, to derive it. Example 2, the infinite wire. All right, in magnetism 1, we already learned it was mu 0 I over 2 pi r. And then we derive that with Biot-Savart law. Ooh, that filled up all the boards. That was a hard calculation. Now we do it with Ampere's law, and it turns out to be very easy. So we got infinite wire, straight, current going like this. So what I have to do is imagine an Amperian loop. Just like with Gauss's law, you have to pick the Ampere loop in such a way that it helps you to figure out the magnetic field. You would not use a rectangular loop, you would use a circular loop. And the reason why is, well, let me move on and I'll explain why we picked the circular loop. So I write out Ampere's law for this loop over here. And then, because I picked this circular loop rather than the rectangular loop, I already know a little bit about the magnetic field around an infinite wire from the Biot-Savart law. I know that at this radius, all along, the magnetic field has the same value because all of these points are the same distance from the center where the wire is. So B is a constant all along. Furthermore, I know from my right-hand rule that B will run along the surface here, or along this arc. And that means that this dot product is just 1. B ds without vectors, right away. The dot product goes away. The B is constant, so it can come out the integral. On this side, I have all the current going through my Amperian loop. So then I'm integrating ds around a circle, which is just the circumference of the circle, 2 pi r, okay? And then I just solve for B by dividing. There are really only 3 lines in this integral. I put this here just so you can kind of see more of the thinking behind why the B came out and where the 2 pi r came from, that we're integrating ds around a circle. But when you're deriving this, you don't have to write that second line here. You could just go boom, 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 3 lines, and you're done. You have Ampere, the magnetic field around an infinite wire. Okay, so that's example 2. All right, let's move on to example 3. Okay. Oh yeah, I didn't create a pause yet, so let me create a pause to give you a chance to copy that down. All right, example 3. Maybe I need another color. Let's see. So I've got a coaxial cable, and we talked about this earlier in the year in electrostatics or with Gauss's law. And what I'm going to have is current coming out of the inner conductor, solid conductor, uniformly distributed over its surface, I. And then I've got an equal amount of current, an equal amount of amperage going in this outer conductor. So the net current in the whole arrangement is actually 0. So I want to find the magnetic field in all regions. Where I'm going to begin is the inner region, which, by the way, this is R, 2R, and 3R are the 3 critical radii. R, 2R, 3R. So let's begin for R less than capital R. In other words, inside this inner conductor. So what I need to do is pick an Amperian loop because I'm going to apply Ampere's law to find the magnetic field everywhere. The Amperian loop will not be a rectangle. It will be a circle again, so that this can simplify on the left side like here, as I mentioned earlier. Magnetic field will run all along the loop. The dot product is therefore just B ds, just 1. And then B can come out because it's constant along. And then we have just B 2 pi r on the left side. So that's already the thinking. I need to know that I need a circle for my Amperian loop because we have a cylinder here. So let's begin by writing out Ampere's law for this shape. Okay. All right, if you need a moment to catch up, I'll create a pause to allow you to copy this down. All right, let's move on. So the left side always becomes, today, for cylindrical symmetry, B 2 pi r. B times the circumference of the circle. Now, let me maybe lower this a little bit because I may end up being too high. So now, mu is 0. I enclosed. So what I have to do is figure out the portion of the current that's going through my loop. It's obviously something less than I, like maybe 0.9 or 0.7 I. But I need to figure out exactly how much by using the idea of current density. Current density times area inside of our Amperian loop. So the current density will be total current over total area of where the current is distributed, which is through this entire inner conductor. So the total area is pi r squared. That's the current density, the amps per meter squared in that inner conductor. To get the amps, I now have to multiply them by the meters squared of my Amperian loop. In other words, the area of my Amperian loop, which is just the area of a circle. Pi r squared, the area of a circle. So those are the two formulas that you're going to use throughout cylindrical symmetry. Circumference is 2 pi r. Area is pi r squared for a circle. All right, so all we have to do now is touch this up and simplify. So the pi's on this side cancel, and I can divide both sides by the r, which makes this to the 1 power, and then I get B is mu 0 You could have this all as one fraction. I just always like having the constants in the front and all the other terms on the right, right to the right of it. But again, one fraction is fine. Unit check. So the last example, it was the formula. We didn't have to do a unit check. But as in Gauss's law and in the Biot-Savart law, I recommend that you analyze the units to see if this formula makes sense in terms of the form. So remember, we're comparing it to mu 0 I over 2 pi r. In other words, we need mu 0 amps over meters for units. We've got our mu 0, good. Then we've got amps times meters on the top, I times radius, all over meters squared on the bottom. And you see that the meters squared on the bottom and the meters on top, so we just have mu 0 amps over meters. We have the right units, so our formula appears to be correct. Okay, so that's part one. The magnetic field inside this conductor, it's 0 at the center of the conductor, and then it grows linearly outward and reaches a maximum value at the surface of that conductor. All right, now, between these two conductors. So in other words, we would write that mathematically by saying we are greater than capital R, but less than 2R. So I would create an Amperian loop. Let's see. I guess I could try green, like this. Oh, I forgot a couple dotted lines here. This is the inner surface. This is the inner surface. So my Amperian loop will be something like this. Okay, so All right, so the left side of Ampere's law, again, is just B times the length of our Amperean loop. In other words, the circumference of a circle. So we can say B times 2 pi r. The right side, well, this is easy. I've just enclosed the inner conductor, not any part of the outer conductor, because the outer conductor is beyond our Amperean radius. So none of this outer eye goes through that green circle, only this eye right here of the inner conductor. So we just have mu 0 I. So we divide by 2 pi r. And we have the magnetic field around an infinitely long straight wire. Okay, so that's that. Now, the third part, I think I won't be able to fit into this narrow part. So let me create a pause, allow you to copy this down, and then I'm going to erase this to make some room. So go ahead and copy. All right, so let me make some room. All right. Okay. All right, so for we're going to be greater than 2r, but less than 3r. In other words, inside this outer conductor. So I need to make an Amperean loop. Maybe I'll use red again. The other colors don't show up so well. So there's our new Amperean loop, a circle that's within this range of radii. So let's begin with Ampere's law. We begin by writing it out. Again, you're not missing any little symbol. The dot product, the vectors, the circle, and the integral, all critical mathematically for saying the right idea. All right, so the left side, once again, we know the magnetic field will lie along a circle, and it'll be constant along that circle. So the left side just is B times the circumference, or 2 pi r. You know, I should lower this a little bit because I'm going to have some fractions here. All right. So now we have the mu 0. Now, what's the current enclosed in this Amperean loop? First of all, the inner current, this I, is completely enclosed. So we can just write I. This is from the inner conductor. But when you look at the outer conductor, you should be able to see that the current going the other way, not all of it goes into our Amperean loop. Only some of it right here and here. And some of it passes outside of the loop, so it doesn't enter into our Amperean calculation. So we need to find the amount of current that passes through this loop that comes from this outer eye. And it goes the opposite way, so I'll put a minus sign for that current. And I need to use the concept of J times area. So first thing I need is the current density. Maybe I'll need some brackets here. So current density will be total current over the area that which this current is going through in this outer conductor. So we have I going this way. But what's the area that it goes through? Well, we have to first find the area of this entire circle here, which is pi times 3r squared. But the current doesn't go all throughout this whole area because it stops at this hole. So we need to subtract off the area of the hole here. So we just get the area right here. And the area of the hole is pi r squared, but the r is 2r. There. There is the current density of the current in this outer conductor. But we need to multiply by the area that's within our Amperian loop. So we're going to take the area of the circle that's our Amperian loop, which is pi r squared. Okay. But that current, that's this density, doesn't go through the whole Amperian loop. It only goes through this portion. But that pi r squared is the area of the whole loop. So we've got to subtract off the hole here again, which is this hole, which is a circle, pi r squared with that radius. So we've got to subtract off another pi 2r squared. Okay. So all that remains is to simplify things a little bit and get to a final answer for the magnetic field, which is what we're after. First of all of these terms here, we've got, all the pi's here cancel. So we can eliminate these set of pi's. We've got pi, 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 all gone. We've got 9r squared minus 4r squared, which is 9 minus 4 is 5. So and you know what I'm going to do is I'm going to factor out the I. So that'll leave me in the brackets 1. And then over here, that I is gone. So on the top, what I have is r squared minus 5r squared. I mean, r squared divided by 5r squared. And then 4r squared. And we've got minus minus, which will make a plus. So you see just a lot of details to keep track of, easy to mess up. And then over here, this is again 5r squared. So hopefully I didn't make any mistakes, sort of simplifying all those parentheses. Now we'll divide by 2 pi, giving us mu 0 over 2 pi over here. And then also divide by r, which will leave b alone. Maybe I'll lower it a little bit. Mu 0 over 2 pi, and then inside parentheses, 1 divided by r. Divide this by r, which gets rid, you know what, before I do that, I just thought of something else. I want to do this 5r squared over 5r squared to find a common denominator between these two terms, which gives us, why do over the r squared? The r squareds cancel. So this is 4/5 and 5/5 added together gives us 9/5 divided by this r. And then here, this r squared divided by that r gives us r over 5r squared. All right, there is the magnetic field inside this outer cylinder. Unit check. This is much more complicated than even the last formula I erased. So what we need to do is have ultimately units of mu 0 amps over meters for magnetic field. We've got our mu 0. That's good. Then over here, we've got, oh, see, there, lost the I. Well, maybe. Let's do. Okay, so we've got our mu 0 amps. And then we've got 1 over meters here, and meters over meters squared, which is 1 over meters minus 1 over meters minus 1 over meters, which is just 1 over meters. And so our formula checks out after I caught the mistake of dropping the I. All right, so go ahead and copy this down. I'll create a little pause. All right, one last region, but don't worry, it's easy. For R greater than 3R, we can apply Ampere's law. But now I make a loop, an Amperian loop that goes around all the cylinders. And when I look at the I enclosed, I've got positive current, negative current, zero current enclosed in an Amperian loop that goes around everything. So the right side is 0. And I ran out of room here, so I'll just tuck it in right over here. B equals 0 outside, but you could do it right below. And that's the magnetic field in that region. So let me create another pause to allow you to copy this down. Okay, one last thing. As you know, with Gauss's law, very often what we did when we found the electric field in all different kinds of regions is we created a graph for all radii, the electric field. We're going to do that now for the magnetic field caused by this coaxial cable in all regions. So let me preserve that formula. The other formula, which you have in your notes, was, I'll just jot it down. This. And then the standard mu 0 I over 2 pi r in between. So these three, actually 4, we plot, set up some axes, and then B over here, R, 2R, 3R, all of our transition values at the various points when we move from one conductor to another. So inside this, we derive this formula. You can see that it's linear, R to the 1 power, R is in the numerator to the 1 power. That means we begin at 0 and rise up linearly. Now, as always, I recommend writing proportional to R in case you didn't draw the line perfectly straight. Whoever's grading the test will see that you know that that should be a straight line. Outside, once we come out of this inner conductor, then in here, in this space right here, it's the 1 over R graph. So that means when we're going out, the magnetic field will get smaller and smaller and reach exactly half the value at twice the radius. So we'll have a curve like this, and I'll put proportional to 1 over R, because again, we had the formula which I had to erase, mu 0 I over 2 pi r between the conductors. So that's that graph. Now, between these, inside here, it's this function. And ultimately, it has to get down to 0 out here. So this is not a straight line. Most likely, well, it's definitely a curve. So maybe you think it goes like this. Maybe you think it goes like that. It doesn't matter. The AP will not get that picky. You could pick either one. But as I mentioned earlier with electric field, what you could do is you could just look at the R dependence here and quickly take the derivative twice with respect to R to determine whether this function is concave up or concave down. For example, forget about all the constants. We've got 1 over R, or R to the minus 1. That's this first term. And then this is minus r to the 1 power. So if I take the derivative of this twice, then I have minus 1 r to the minus 2 minus 1. Take the derivative again. Minus 2 times minus 1 gives me 2 r to the minus 3. And then the derivative of 1 is 0. And so you see that this is positive. The function is indeed concave up. So, and it should be continuous. So something like that. All right. We could also put transition values here by possibly plugging in capital R into this formula, which just gives us mu 0 I over 2 pi capital R. And we could figure out this transition value by plugging in into this formula 2 capital R, which would give us mu 0 I over 4 pi r squared, or 4 pi r, sorry. There's the magnetic field at that second transition. All right, so let me create a pause to give you a chance to catch up copying that graph if you need to. All right, so that's Ampere's law 1. We learned the concept, B ds closed integral around some kind of loop equals mu 0 I enclosed. So you need to know exactly how that concept works to apply it to all kinds of shapes of currents and Ampere loops. Then we looked at two other examples, the magnetic field around an infinitely long wire. We derived mu 0 I over 2 pi r again with Ampere's law, really quick and easy. It was nice, right? And then we looked at this coaxial cable, and it was a little bit more involved. But again, we did the magnetic field in all 4 regions, and we plotted, again, using Ampere's law. The left side is always, for cylindrical symmetry, turns into B times 2 pi r. And then the I enclosed can get a little tricky with J times area, current density times area. That'll be the I enclosed in the Ampere loop. All right, so I hope you learned a lot. I hope you enjoyed. I'll see you in the next physics video where we'll look at another example of Ampere's law.